Okay, so we have some more derivatives that we want to work out, and these ones are looking a little bit more complicated, but there's tricks to these. So this is where your algebra skills are extremely important. You should have pretty much mastery over algebraic manipulations of expressions because you need them all here in calculus. So starting with this first function, what we have here is kind of an exotic looking function. We have a bunch of power functions over another power function. And when we kind of look at things in this form, we think, okay, it looks like I need to take the derivative of a function divided by another function. But there wasn't a rule for that in our table of rules. There does exist a rule for that. It's called the quotient rule, and I believe we talk about that in the next section. But since we're not there yet, we can't be expected to use that yet. So in this case, we can actually simplify things a good amount to make this much more doable. I'm going to rewrite everything in my numerator in terms of exponents. Now, 2 of these are already written as exponents, but that 4th root of x is not. So I'm going to rewrite that as x to the 1/4 power minus 7x squared plus 9x to the power of 2.4. All over x cubed. Okay? Now this, I can separate this out into 3 separate rational expressions. I can write this as x to the 1/4 over x cubed minus 7x squared over x cubed plus 9x to the 2.4 power over x cubed. I have a common denominator here, so if I was going to go back a step, I'd add these all together into a single rational expression where that same common denominator is what I have there. But I'm doing the opposite. I'm separating it out. The reason I wanted to do that is because I can simplify each of these using a property of exponents. If I have x to a power over x to another power, that's equal to x to the power that I would get by subtracting these exponents, doing the top one minus the bottom one. So 1/4 minus 1/3 is what I'm doing there. Okay. 1/4 minus 3. I think I said 1/4 minus 1/3. I said that wrong. 3 is the same thing as 12/4. So 1/4 minus 12/4 is negative 11/4. Here, same idea. I have minus 7. And then 2 minus 3 is negative 1. So 7x to the negative 1 power. Plus, here we have 9x to the 2.4. So the 9 is going to stay put. And then I'm going to do 2.4 minus 3. That's x to the power of negative 0.6. Okay? Now at this step, what I'm going to do is take the derivative. I've been writing y prime a lot, but I can also use this notation, dy dx. So I'm going to switch it up a little bit. The derivative is just applying the power rule to each one of these. So power rule here, the negative 11/4 comes down, and then I get x to the power of negative 11/4 minus 1. That's the same thing as minus 4/4 to get a common denominator there. 11 minus 4 is, or negative 11 minus 4 is negative 15, so I would get x to the negative 15/4. That's the derivative of that first term. Moving on to the next term, negative 1, it's going to come down, multiply to the negative 7 to give me a positive 7, x to the negative 2nd power. Finally, down here, negative 0.6 times 9, that's equal to negative 5.4 x, and then I subtract 1 from this. That's going to be negative 1.6. Negative 5.4 times x to the negative 1/6 power. This guy right here is, kind of cut off my negative there. That's my derivative. Okay. Now, I have all of these negative exponents here. You may want to go and rewrite this as 1 over this to the positive 15/4 or whatever. You don't need to. You can leave them as negative exponents. I'm fine with that. I would prefer just to have my answer written this way. Okay, got to do this again. Next one, f of x equals 5 over x. We can try and take a derivative right away, but you're going to run into a little bit of trouble because, again, it looks like a quotient of things. So you want to rewrite your function in a form that matches some combination of those derivative rules. This is the same thing as 5 times x to the negative 1 power. Okay, and hopefully you can see why that's the case. But what I'm doing is rewriting this as a constant times a power function, which we know how to deal with those. F prime of x, using my power rule, the negative 1 will come down and give me a negative 5, x to the negative 2nd power. I can either leave it like this, or I can write this as negative 5 over x squared. Either answer is fine. That one was much faster. Okay, here comes another one. Y equals x squared minus 5, in parentheses, times quantity 3x plus 8. So this is a derivative of a product of two functions. Now we do have a technique for doing this where you have the product of two differentiable functions, and how do we take the derivative of those? It's called the product rule, but that's also something that we don't talk about until the next section. So how do you approach this? How do we deal with the derivative of this product if we don't have the product rule yet? And the answer is to just multiply this out before taking a derivative. So if I were to distribute everything, I'm going to get x squared times 3x, that's 3x cubed. X squared times 8, 8x squared. Negative 5 times 3x, that's minus 15x. Negative 5 times 8, which is negative 40. And now we can find our derivative. I'll use another dy dx for this one. So it's a polynomial, which means I'm just doing repeated applications of the power rule. Power rule here, 3 comes down, times that 3 there, makes 9x, and then I subtract 1 from the exponent, squared. Here, bring the 2 down, 2 times 8 is 16, subtract 1 from the exponent, becomes x to the power of 1, which is just x. Here, you can either use the power rule, or you can remember that special case of the power rule, which said that if you're taking the derivative of just x, that's just equal to 1. And that was, again, special case of the power rule. So if that x becomes a 1 times negative 15, I'm just left with negative 15. Finally, this constant is going to disappear because its derivative is 0. And there's no real point in writing plus 0 here because it's the same thing. So this is what we got in that case. Okay, it's much, much nicer doing derivatives this way. All right, let's do another example, but this time we'll use the derivative for something specific. So here, we want to find the slope of a line that's tangent to a graph of y equals 2 to the power of x plus 4x at x equals 1. Okay, so this is an interesting function because it's a combination of two different types of functions that we're adding together. So the graph won't look just like an exponential function. It also won't look just like a line, but the sum of those things somehow gives us a graph that mixes those two. We're not going to draw the graph at all. Even though it's referencing the graph, we have enough information to do this without a graph. So we know that the slope of a tangent line to a graph can be found using the derivative of our function. I'm going to find y prime. Y prime, I have a sum of two functions, so we take the derivative of each term separately. The derivative of 2 to the x is the natural log of 2 times 2 to the x. Remember, it's a constant times itself. Plus, remember, if you have some constant times x, the constant is what's left behind. We saw that in the previous example. So it's the natural log of 2 times 2 to the x plus 4. We want the slope of the tangent line at a specific value. We want it when x is equal to 1. So I'm going to plug 1 in for x here. That's going to give me ln of 2 times 2 to the power of 1 plus 4. Okay? This I can just write this way. 2 natural log of 2 plus 4. I can leave it in that form, or if I want, I can make it a tad bit simpler by using that logarithm property that says this constant can be brought up into the exponent of that 2 right there. making it 2 squared or 4. So I could alternatively write this as my solution. Natural log of 4 plus 4. I'm not plugging anything into a calculator. I want to keep it in this form. The time when I want to plug stuff into a calculator is in an application problem, which we're about to do next. Okay, because we kind of want answers that are coming out to dollars and cents, that kind of a thing. So let's take a look at this example here. A company has a price demand function given by P of X equals 250 times 0.995 to the power of X. That's the price in dollars of each item when X items are sold. We want to find the rate of change of price with respect to demand. And remember, that's when we say demand, we mean how many items were sold. So it's with respect to X specifically. And in fact, I'll just do this. Demand is referring to X. When 215 items are demanded, and interpret your answer. So it's specifically asking for a rate of change of price with respect to demand. And price is just this function by itself. So far, when we've encountered these price demand functions, what we've typically been doing is using them to find a revenue function. And a revenue function is X times that P of X. But we don't want a revenue function. We specifically just want price. So I'm going to start by taking a derivative of this. So P prime. Okay. Now thinking about our derivative rules, we have a constant times an exponential function. The constant, because of the constant multiple rule, basically just stays put, and we just move over here and take the derivative of that exponential function. So I'm going to get 250 times the derivative of this exponential function, which remember is itself 0.995 to the power of X, but then times the natural log of the base of that exponential, so 0.995, natural log of that. Okay, that's the derivative. But we want the derivative specifically when X is equal to 215. So I'm going to now plug a 215 in to this function. 250 times 0.995. This is where the 215 goes, right there, times the natural log of 0.995. This is one that you would want to plug into a calculator because, again, it's an application problem. We want dollars and cents here. If I plug it into a calculator, I'm going to get approximately negative 0.43. Okay? Now, how do we interpret this? Well, it's a rate of change, first of all, in our price, and it's negative. So what that indicates is that we're seeing a decrease in our price, specifically because that's what the negative is showing us. And the decrease is specifically 43 cents per item sold. So it asks us here to interpret our answer. We can say this: when 215 items are sold, or it uses the term demanded in the phrasing of the problem, then the price per item is decreasing at a rate of 43 cents per item. Okay? Again, that's how we interpret that negative. It's a decrease in price as opposed to an increase. All right, let's keep moving. Here's another example where we're going to use values of particular functions that are in a table. So we have these two functions, f of x and g of x, and then we have their derivatives, f prime of x and g prime of x. But we don't know what the functions look like as, an algebraic sort of representation. We just have some information about these. Turns out that that's all the information that we need. So based on this table, we want to find the following. If we define this function h of x to be equal to 2 times f of x minus 5 times g of x, it's asking us to find h prime of 0. Well, you can't find h prime of anything until you find h prime of x first. So for part A, we're going to start by finding h prime of x. h prime of x is defined as a difference of two constant multiple functions. So I'm going to take its derivative by keeping the constant 2 alone, taking the derivative of f, 2 times f prime, minus 5 times g prime of x. This is what the derivative of h would be since we're defining h this way. Once I know that, to find h prime of 0, I'm just plugging 0 in for these x's. So h prime of 0 is equal to 2 times f prime of 0 minus 5 times g prime of 0. But both of these, h prime of 0 and g prime of 0, are things that we can find in this table. So for an x value of 0, that means we're in the second row here, f prime and g prime. So f prime is negative 1. G prime of 0 is 0. So this is equal to 2 times negative 1 minus 5 times 0, or just negative 2. Okay? That's it for that one. What about part B? So part B says, if m of x is defined to be f of x plus g of x over 2 plus 5x squared, find m prime of 4. Okay, so another way of writing that is this. M of x is equal to 1/2 times f of x plus g of x plus 5x squared. So that means m prime can be found by doing a combination of our derivative rules. I have a constant times a function, so its derivative is the constant times the derivative of that function. But that function that I'm referring to is actually a sum of two other functions, f of x plus g of x. Its derivative is just f prime plus g prime. So I'm going to get 1/2 times f prime of x plus g prime of x. I also have this term over here, which I need to take a derivative of, but this one is not defined in terms of either f or g. It's its own thing, 5x squared. That I just use the power rule on. I would get 10x as a result. Okay, now we have enough information to find m prime of 4 specifically. That's 1/2 times f prime of 4 plus g prime of 4 plus 10 times 4, because again, we plug a 4 everywhere in everywhere that we see an x. Obviously that's 40, but what about these other two values here? Well, f prime of 4 and g prime of 4 are both in our table. 4 is this third row. F prime gives me 3, g prime gives me 16. So plugging those things in, I get 1/2 times 3 plus 16 plus, that's 40, okay? 3 times 16 is 19. 19 times 1/2 is 9.5, so that becomes 9.5 plus 40, which is just 49.5. Okay? Again, we're using those derivative rules and then pulling values from a table after we have written things after applying those rules. So not super complicated, just kind of a different angle we could take on that type of a function or type of a derivative problem. Here is another perspective, another way that we can look at these types of examples. Instead of having a table of values, I have graphs of functions. It says the graph of f, the blue function, and g, the red function, are given on the same set of coordinate axes below. Use the graph to find the following. So I need to find g of -3 plus 2 f prime of 0. Notice only one of those things has a prime on there. Only one of them is a derivative. The other one is just a function. So let's see. What is g of -3? Well, for this, I would literally find -3 on my x-axis and find the point that corresponds to that on the graph of g. The output there is a 6. So that is 6. Okay? Plus 2 times f prime of 0. How do we find f prime of 0? Well, if you notice, first of all, f is this blue graph, and we can't just plug 0 in and say, oh, look, it's 5, because that's what f of 0 is, not f prime of 0. F prime of 0 would give me the slope of the tangent line to this function at that value. So really what I want is the slope there. Now it's convenient that this graph here is just a line, because any tangent line to that line will have the same slope as the line. So if I can just find the slope of this line, I'll be in good shape. The easiest way to do that, if you notice there's a grid in the background, look for points where this blue line crosses through a corner of grid lines. So you notice there's a corner right here of these two grid lines, and it intersects that blue line. And then I have another one up here that intersects it. I can use those 2 points to find the slope of this line right here. From this leftmost point to that rightmost point, I'm going up 2 units and to the right 1 unit. So rise over run is 2 over 1. That makes the slope 2. So f prime of 0, because it's part of that line, is just 2. That gives me 6 plus 4, or 10. Okay? Not complicated. You just need to know how to make sense of the graph and how to find slopes using a graph. Next step. If h of x is equal to f of x plus g of x minus e to the power of x, find h prime of 3. So for this one, we start by finding h prime of x, just like the previous examples. That would be f prime of x plus g prime of x. And then remember, e to the x is its own derivative, so I get minus e to the x. Nothing changes about that. If I want to find h prime of 3 specifically, then I'm plugging 3's in everywhere. F prime of 3 plus g prime of 3 minus e to the power of 3. Okay, now both of these are derivatives, f prime and g prime, which means I don't have the graph of either of these shown explicitly, but I do have the graph of f and I do have the graph of g, and so these represent slopes of tangent lines to each of those graphs at x equals 3. And conveniently, if you look at where x is equal to 3, both graphs have a horizontal tangent line there. So this one, for g of x, the entire graph is just a horizontal line anyways, at least for the part that, x equals 3 is on. For f of x, it's not a constant function, but it has this like valley bottom right there, which would give me a horizontal tangent right there. That would also have a slope of 0. Both of these are equal to 0 because both of them are horizontal tangents. So I have 0 plus 0 minus e to the third power, which is just negative e cubed. Don't bother plugging that into a calculator. Leave it in that form. That's kind of preferable. Okay, I'm going to stop this video here. We should be able to knock out the rest of this section in the next video.